Good morning everyone. Today my topic is Best Engineering Design Practice for Jet and Pool Fire in Oil and Gas Industry. Agenda. We will start with background of the article, then objective of the paper, followed by proposed heat flux values for jet fire, proposed heat flux equation for the pool fire, proposed depressurization time, at the end pool fire calculation using API 521. Why suddenly something new when we have API 521 in place? The first guideline for design and protection of pressure system to withstand severe fire by Institute of Petroleum London, and this is the cover page of Institute of Petroleum London. The second guideline for protection of pressurized systems exposed to fire by Scandpower of State Oil, and this is the cover page of State Oil. These two guidelines discuss the application and the limitations of API 521 as follows. So all process and safety engineers need to study both the guidelines as it covers the various safety design aspects for oil and gas units. The success or failure of protecting plant facilities from fire using pressure relieving system is purely depends on following assumptions: the type of the fire and the size of the fire, as above to determine the heat flux intensity and the fire coverage area. These are the pictures of the pool fire, and these are the pictures of the jet fire. API 521 covers the following fire scenario: open pool fire or fuel control pool fire. This is mainly for refinery and chemical plant, which means small to medium size of the fire. In open or fuel control fire, air is in excess while hydrocarbon fuel is limited. Example is fire on open ground. For confined or ventilator control fire, air is limited while hydrocarbon fuel is in excess. Example is fire inside the building. API 521 does not cover following fire scenario: confined pool fire, big pool fire, open jet fire, confined jet fire, serial fire or any other fire. For above types of the fire, API will not ensure fully safe design, as the failure mechanism, heat flux intensity and the fire area are much different than open pool fire. In case of high pressure oil and gas unit, jet fire may be governed, and jet fire is the main cause for the local failure. API 521 mainly concentrate on overpressure failure and its prevention. API 521 indirectly talks about local failure, but API 521 does not specify any specific requirements for local failure analysis of process components. These process components are vessels and the pipes. The local failure is due to high local heat flux, wherein component engulfs in the flame of pool fire or component impinged by the jet flame. The gas process segment or the thin process segment can fail easily due to high local heat flux. API 521 is silent on protecting weak process segment by pacifier protection. These segments are thin pipes, bend, flange joints, pump seal, control valve, abnormal pipe expansion due to the fire. API 521 is also silent on protecting non-process segment by pacifier protection. These segments are pipe flange bolts, pipe and vessel supports, structure supporting all process segments. The failure of dry or weak process segments and other non-process segments cannot be eliminated using either depressurizing or relief system. This component can be protected by pacifier protection or by any other means. IP and Scandpower provides detailed guidelines for the same. Objectives of first two sections: to study the behavior of pool and jet fire from the results of 10 large-scale experiments and compare these results with the various industry standards. The experimental results can be used to validate CFD, fire release equation and the design guidelines. This section summarizes the applications and the limitations of heat flux listed in different standards. Finally, author suggests the modified equation to calculate absorbed heat duty for the pool fire and the jet fire. Objective of third section. Understand the requirement of 8 minutes depressurization time as against 15 minutes stated in API 521. Objective of fourth section. This section summarizes how to use API 521 correctly and effectively. First section. Propose heat flux values for the jet fire. Experiment number 3 for the jet fire. As per this experiment, the average heat flux over the flame impinged area for sonic natural gas jet fire is 200 kW per meter square, while for two-phase propane jet fire is 150 kW per meter square. And this is the average heat flux diagram for the jet fire. Experiment number 10. The jet fire on a horizontal LPG tank. The total average incident heat flux was 170 kW per meter square. As per IP guideline for the open jet fire, heat flux ranges from 100 to 400 kW per meter square. Based on previous experiment, we have chosen 150 kW per meter square. And for the confined jet fire, heat flux ranges from 150 to 400 kW per meter square. Thus, average has been selected as a 200 kW per meter square. Based on experiment number 3, 5, 6, 10 and IP guideline, authors suggest the global average heat flux value of 150 kW per meter square for the open jet fire and the minimum 200 kW per meter square for confined jet fire. However, the 150 kW per meter square of global average heat flux should be used carefully with the appropriate values of wetted area and a fire duration as advised by safety specialists. Alternately, the design consultant shall perform detailed CFD analysis to estimate heat flux distribution. For open jet fire, the 100 kW per meter square of global average heat flux recommended by Scandpower and the NOSCO is on a lower side as shown in the below table. Second section. Propose heat flux equation for the pool fire. As per IP guideline for open pool fire, the heat flux ranges from 50 to 150 kW per meter square. Thus, the average has been selected as 100 kW per meter square. As per Scandpower guideline for the pool fire, the global average heat load is 100 kW per meter square. Kerosene pool fire on LPG tank. The 5-ton horizontal LPG tank was engulfed in a kerosene pool fire. The size of the pool fire was 4 by 7 meters. The maximum heat flux of 100 kW per meter square was reached within 3 minutes. For a major hydrocarbon, heat flux is around 100 kW per meter square as shown on this slide. And for refrigerated hydrocarbon, heat flux is more than 200 kW per meter square. This is a famous API 521 equation for the pool fire, whereas Q is the absorbed heat duty in kilowatts, C1 is for inadequate drainage and firefighting system, C2 is for adequate drainage and firefighting system. A is the wetted area in meter square, F is the environmental factor as specified in API 521. Based on experimental result and above guidelines, the proposed constant, the C1 and C2, for the pool fire and the confined pool fire are as follows. The red value indicates the proposed constant while the blue value indicates the API constant. The proposed constants are much higher than API constant. Thus, the high heat input to the process unit is expected. Thus, API design may not be adequate at all the times. Third section. Proposed depressurization time for the jet fire and fully angled pool fire. The depressurization time as per Scandpower and IP guidelines is only 8 minutes as compared to 15 minutes stated in API 521. Why? The following are temperature contours of kerosene pool fire in a circular band of 20 meter diameter. The 800 degrees Celsius contour represents the flame envelope. The equipment in the pipe covered in the flame envelope will attain high temperature within a short time and it fails quickly and further become a source of the fire. Natural gas jet fire experiment on pipe, and this is the temperature rise graph under jet fire. You can clearly see that for initial 8 minutes, temperature rise is 180 degrees Celsius per minute. Thus, the metal attains 500 degrees Celsius temperature within 4 minutes and 1000 degrees Celsius in 12 minutes. The rate of temperature rise for a dry system is 100 to 200 degrees Celsius per minute, and material strength falls rapidly once the temperature exceeds 500 degrees Celsius. As observed in the previous experiment, the metal can attain 500 degrees Celsius temperature within a short time. And weak section like thin pipes, flange joint, bands and support may fail quickly under the high temperature of flame as compared to the thick vessels. If these weak sections are not protected with PFP or by any other means, then 8-minute depressurization time is well justified as against 15 minutes stated in API 521. Otherwise, fourth section, full fire calculation using API 521. Use API equation to calculate absorbed heat duty. And average heat flux is equal to absorbed heat duty divided by weighted area. All these constants we have already discussed in the previous section. The weighted area raised to 0.82 indicates the larger the area of the container, the less likelihood the tank will be fully exposed to radiation. As compared to the top and the side section of the tank, bottom section sees high radiation. Thus, the larger the surface area of the tank shell, the lower the average heat flux. From this table, we can clearly see that the heat duty increases with the weighted area, while the average heat flux decreases with the weighted area. It means for a higher weighted area, heat input per unit area is decreasing. Let us take example of single blowdown valve which is serving two vessels which are spread over the ground. Each vessel is engulfed individually in the flame and each has 10 meter square weighted area. We can calculate the heat duty by two methods. In method 1, first we calculate total weighted area and then find the heat duty. And the heat duty is 504 kilowatts. The second method, we calculate the heat duty for individual vessel and then add all heat duties. And by the second method, we get 571 kilowatts heat duty. The first method, the total area represents the one big vessel, thus heat input by first method is less compared to second method. Similarly, do not split the weighted area for cells, heads and piping which can be engulfed in a single flame, as this will give higher heat duty than the actual required. Thus, for this example, method 1 is the correct method. In Addendum May 2008, API has introduced new constant for the air cooler tubes. The C1 and C2 constant for air coolers are much higher than API equipment, and weighted area factor is 1 instead of 0.82, which means high heat input to the air cooler is expected as tubes are fully engulfed in the flame as compared to the other equipment. The average heat flux remains constant as all the tubes are exposed to same level of radiation. Thus, Z is equal to the 1. The air cooler heat duty is 2 to 3 times bigger than vessel heat duty. Thus, the lines and the small filter laid on the ground should use air cooler constant as they are fully engulfed in the flame. Following conservative practice should be avoided for weighted surface area calculations. Application of pool fire for the graded offshore platform should be avoided, as the graded offshore platform cannot hold liquid pool. Application of pool fire for gas platform should be avoided as it does not have any liquid. The weighted area about 20 feet of the pool fire should be avoided. It has been observed that without checking equipment elevation, weighted area is calculated for heat duty. Similarly, the bottom of the vertical vessel covered with the skirt support should be excluded from the weighted area, as fire cannot reach to the bottom of the vessel under the skirt support. The top vapor outlet line must be excluded from the wetted area. The free draining line should be excluded from the wetted area, as during a fire blowdown, all inlets and outlets lines are closed and liquid lines drain into the vessel. Thus, for the practical purpose, those liquid lines are non-wetted at the time of the fire. Heavy crudes, high boiling liquids. For heavy liquids, simulation may not show any boiling at relieving pressure. This will be misleading. There are two possibilities for high boiling liquids. First possibility, instead of liquid boiling, liquid can start cracking into light gas and overpressure the vessel. The appropriate condition for cracking should be considered to find a vapor release load. Second possibility, the gas blowdown system cannot remove liquid into the flash system, and thus the major liquid remains inside the system. Vessel may fail due to long exposure of high local heat flux, and oil will leak into the fire, adding more fuel to the fire. If economics and layout permits, then one may consider liquid blowdown system transferring liquid to the remote or underground location. Wide versus narrow boiling liquid. Sizing of relief device for wide boiling liquids are different as latent heat of evaporation and the gas molecular weight varies significantly over the time, while in case of narrow boiling liquids, both remains constant. Thus, for the wide boiling liquids in a large quantity, series of flash shall be considered for a fire duration. For practical conservative case to be considered for PFC sizing. Degassing and dissolution liquid. Vapors that are physically or chemically absorbed in the solution will be liberated from liquid upon fire heating, and this is not a standard latent heat, but it is known as degassing or dissolution. Use HISIS or other simulation tool to find vapor relieving rate to account this effect. Examples of degassing liquids. The rich amine saturated with H2S and CO2, rich TG saturated with water, but amine or TG itself cannot vaporize, but rich amine will liberate H2S and CO2 under fire heating. Thus, use simulation tool to find vapor relieving rate to account of both effects. Thank you. Bye-bye.